So we have these 4 vocabulary topics, 3 sets of terms and 1 phrase that I want to make sure are in your vocabulary. So if you can make sure you get those typed up first. So get those 3 phrases in there first, and then we're going to add detail to them. So first thing we're starting off with is base case. Then we're going to talk about recursive call, infinite recursion, and the difference from a loop with recursion. So those 4 things are the first things we're addressing today. All right. Okay, let's go ahead and let's start with base case. Our base case is the stopping point of recursion. So the base case is when we stop. The base case is when you stop your recursion. Recursion is a process that continues. It is a process that happens over and over again. And so the base case is the stopping point. The other option in recursion is the recursive case. So the base case is the stopping point. The recursive case means we do it again. I didn't put recursive case on here because we have recursive call, because it's going to be, you are calling a method every time we do the recursive case. So the base case is the first case we define. We want to stop our recursion. Now, as I mentioned last time, recursion is really nothing new in code. It consists of 2 parts. An if test and a method call. The base case is if you pass the if test. If you pass the if test, if the if test is successful, you are at the base case. If you do not pass the if test, you fail the test, then you go to the recursive case. So the base case is if you are successful in passing the if test for recursion. So the if test means, oh, am I done yet? Yes or no. I failed the if test, I'm not done yet, I continue going. I passed the if test, I am done. So the if test, a successful if test, means we've achieved the base case. We are stopping recursion. And all recursion is, again, is an if test with a method call. Nothing new in code. The recursive call is when we call our method again. So we've written methods time and time again. We've written lots of methods. A recursive call, however, is when we call a method inside the same method. So I have a method called toast. Public int toast is my header, with an int x as a parameter. Now, this is just a regular method for all we can see right now. There is nothing special about it. That's just a regular method header, because recursion is not special code. Recursion, however, is code that requires us to think a bit, to plan. If we don't plan in recursion, we will keep recurring and recurring and recurring, and we will achieve the problem of infinite recursion, which crashes your system. It's fantastic. Thumbs up to everyone. So our public int toast, inside a recursive method, we have to have an if test. Oh, no big deal. Okay. Wiggle. If test, inside there. If I pass that test, I have achieved the base case. So the base case happens when I do what? Pass the test. Everyone, the base case happens when we do what? Pass the test. Say it one more time with me, everybody. The base case happens when we pass the test. What kind of test? If test. Okay, so the base case means we do what? We stop. Everyone, the base case means we stop. Base case means what?
We stop.
Stop recursion. We stop recurring. Okay? So the base case means we are done with recursion. And we do that when we pass our if test, if we are successful in passing the if test. If we fail our if test, we have a recursive call, or the recursive case. Recursive call or recursive case are the same thing. A call to a method is when we do what? We do the method, right? So if we have a recursive call, we are calling the recursive method inside the method. And we only do that at what point of code?
Else.
If we have an else. And so our base case has to fail, which means we have to have an else condition on our if test. So recursion requires an if test and a method call. Basic structure. Base case is when?
Pass the if test.
If we pass the if test, and that means we stop recursion. So, base case. When we stop. So, base case. When we stop. We pass the if test. And that is the base case. The base case means we passed the if test, we have stopped recursion. And that means at the same time that we're going to go back and catch the information we've left behind. So the base case means we stop. We are passing the if, and we are going to now catch the information that we left behind. So new stuff. We're not doing anything new in code, but we're calling it and explaining it differently. So make sure you have this down in your notes that the structure, all this code we're doing, there's nothing new code-wise to this. This is all code we've seen and used before. We're just putting it together a little bit differently. Okay, so we've got our base case. The recursive case is when we have failed the if test. We are continuing recursion. And we are generating info. So the recursive case is the inverse or opposite of our base case. It happens when we fail the if, we continue our recursion, and we generate more information. So we have a recursive case, and we have our base case. If we do not plan our recursive case or our base case well, we will achieve infinite recursion, which means our systems will crash. Now, who has at least 4 gigs of RAM in their machine?
Yes.
Okay? So you have a lot of RAM. That, say, for example, 4 gigs fills this room. Okay? Say that was like how much that 4 gigs, if we actually were to put it out, would fill this room. And every time we make a recursive call, we take out a single tablespoon worth of information. Now, a tablespoon is not a lot of volume. There are millions of tablespoons in this classroom.
Trillions.
Maybe trillions, but there are a lot. However, even if we're only taking out a tablespoon of volume, if we have an infinitely recursive problem,
We can empty an ocean.
it would empty an ocean because it would never stop. Because each time I call this method, it would take out that much. But that method gets called by itself. So I would take out this much, which causes me to take out this much, which takes 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 out this much, over and over and over and over and over and over and over again. Which means immediately we could, and since computers do things much faster than people count, we would take up all the space out of this room. Recursion crashes. So recursion requires design and planning. You must design and plan. Specifically, you must design and plan the base case. Your recursive case needs to stop. And that is why when I write my recursion and when you write your recursive methods, the base case is passing the if test. I have successfully reached the end. I'm not at the end yet, I keep going. But we have that end goal in mind is passing the if test. And so we check for that first. Now logically, it doesn't truly matter. We could have the base case be the else. But I want to make sure the base case for us, mentally speaking, logically speaking, is our success. We stop when we pass the test. You might have heard of the phrase, if you're in a hole, stop digging. We want to stop digging at some point. And so that is why our base case is a successful pass on the if. When we reach the base case, we do what? We stop. We stop digging the hole. We are sick. Now, recursion is powerful. It's amazingly cool. You can solve huge, giant problems. We're going to solve a couple simple ones. One, because math. The really cool things that you do to solve recursion with, for the big, cool, nifty stuff, require a fair amount of math. Not hard math, but time math. And we're in a high school class. Time is limited. So we're going to do some cool, nifty things with some numbers.
Sounds very cool and nifty.
I think so. Now, recursion is not efficient. Put that in your notes. Put it in your head. Recursion, not efficient.
Why is that?
But just because something's not efficient doesn't mean we shouldn't use it. It is powerful. Now, who has moved large things before? Okay. Does a big, huge truck that gets 8 to 12 miles a gallon help you move large things?
Yes.
Yes. It's not efficient on gas, but it has a giant towing capacity. And sometimes the giant towing capacity is more important than how much you spend in gas. The same is true with recursion. We're going to make the machine do lots and lots of lifting. And so recursion is powerful, but it burns through resources. Again, design and plan is the key. You use this when you're supposed to, not just because you think it might be nifty. So, the recursion that we're going to look at involves a couple number sequences. We're going to look at 2 of them. The Fibonacci sequence is our first one. Our Fibonacci sequence is a sequence of numbers discovered by an Italian mathematician back in the dawn of time. Not quite, but that's okay. We talked about this right before break. We have a sequence of numbers. What's the next number? 21. What is the structure of the Fibonacci sequence?
Current number out of the previous number makes the next number.
So add 2, previous, or next. Trip and make noise, always good. So we add 2 previous numbers for the next. This can be solved iteratively in a loop, or we can solve it recursively using methods. We are going to do a recursive solution for it. We're going to write it out on the board and then we'll test it out on the machines. Okay, so our Fibonacci sequence. What do we design first when we're designing a recursive solution? The base case. When do we stop? And so by looking at the sequence of numbers, at which point do we stop?
How many digits you want?
When we were at 1. Now, we also are going to have a condition for 0. Because math has identity issues, and we have to actually define what happens at a specific case. And so we're going to say our base case is 0 or 1. Now, this is our 0th spot in our Fibonacci sequence, our first spot in the Fibonacci sequence, our second spot in the Fibonacci sequence, dot, dot, dot. And so we have Fibonacci of 0, Fibonacci of 1, Fibonacci of 2, Fibonacci of 3. And if we do that like this, like f of, f of, f of, f of, hey, look, math. We've seen this before. F of x. F of 1 is 1, f of 0 is 1. F of 1 is 1. F of 2 is 2. F of 3 is 3. But f of 4 is 5. F of 5 is 8. Now, f is a horrible name for a method. It's a legal name, but we won't do that. We're not mean to ourselves like that. So we will make a method that is Fibonacci. And it's a public method, and it's going to return an int. And so our header will be public int Fibonacci int value. Actually, it's not value. Value is bad name. Int
Fib number of joint.
current number. So there's our header. You want that in your notes as well. So our header for our method, public int Fibonacci, int current number. And because, earphones out please you guys. Because we are doing a int method, what is the first and last item of our code? If we have a method that returns an int, we know what our first and last item needs to be. What's our first line of code need to be in a method that returns an int?
Declaration of an int.
Declaration of an int. So we'll say int fib value equals 0. Why do I assign a value inside the method for that int? Why am I giving it a value right now? when I first declare it.
To avoid accidentally returning null.
To avoid returning null, but since it's an int, I can't return null, so I have to give it a value because it's a primitive, and so I have to assign a value to it at the beginning. I have to tell it what its value is because it's inside a method. My last line of an int method is return fib value. So my last value, no matter what, of an int method would be return fib value. So this code will right now work completely. It is not recursive. But again, in keeping with our guiding principle this year of always writing code that works every step of the way, even though it's not recursive, this code will compile and run. And it'll just give us 0. Pretty bad code, but that's okay. But our code will work. So we've got this in your notes. So the first thing we have to do is make our base case. Now, the Fibonacci sequence does not work on negative numbers. So we have to test to make sure that our number is non-negative. So we have that's our first thing we have to check. Before we can even actually figure out the Fibonacci sequence, we have to make sure it's not negative. Now, is 0 negative?
No.
No, but it's not positive either. It's just 0. But that's okay. We can deal with 0. 0 is the 1 value. We're all right. So we have to do a test for non-negative. So what would be a test for non-negative?
Greater than or equal to 0, not less than 0.
So if parens if current value is greater than or equal to 0. Nothing new in code, right? We've tested for greater than or equal to number before. And none of this code right here is in any way, shape, or form new. Now, is this our base case? Is this when we stop?
No.
No, this is just making sure we're not going to error out. Our last line still compiles. If it's greater than 0, nothing happens. Again, we are always making sure our code works the entire way through. So we have f of negative anything is taken care of. We have this magic space of non-existing numbers. Done. F of negative 5 doesn't exist. F of negative 8 billion doesn't exist. But right now, all I do if we get f of 0, we still get 0. And that's not, f of 0 is not 0. F of 1 is definitely not 0. F of 18, definitely not 0. We need to actually have our method call. And so our base case is what we do when we stop. And so we have a new if in here. So inside our existing if, we add our base case if. If our current value is less than or equal to 1. What are the conditions that that if test will catch? Okay, so if the number is greater than or equal to 0, so if the current value is less than or equal to 1, so I'm using a conditional operator here. So this conditional operator will catch everything that's above 0, including 0. This conditional operator will only catch 0 and 1. all it can catch, because we're doing our base case. And so if we have our base case, we need to do something. We need to stop recursion. And if I'm in a method that has an int as its return type, how do I stop that method? How do I get out of that method? What stops a method that has a return type?
Returning.
Return.
The return statement.
A return statement does. So, what I have inside here, and this is really important in your notes, and this is giving us infinite recursion if we do it wrong. But I'm putting this in nice blue letters so you see it, it's different. Return 1. Clearly a 1. So if our current value is less than or equal to 1, I return 1. So I'm catching either 0 or 1, and I've achieved my base case. If I get f of 0 or f of 1, the value I get back is 1. That's the only thing I get back, because I get 1. Now I'm not dealing with the recursive case yet. So this is just the base case. This will stop recursion. If I type in 8 in here, so Fibonacci of 8, fib number is 0. Is current value greater or equal to 0? Yes, because it's 8. Okay. Current number. Let's fix that. Helps when I... Okay, current number is greater than 0, yes, but it's not less than or equal to 1. So what is fib value? 0. So I would return 0 if I type in 8. And fib of 5 is 8. I'm really willing to guess that fib of 8 is not 0. Especially when the rule is add the previous 2 for the next. So if that's the case, then 8 will definitely not be 0. So this method is not recursive yet. This method just gives us 1 if it's 0 or 1. Otherwise, it gives us 0. Not recursive. So in order to get the recursive case, we have to add our else. And again, this is why squiggles are important. Squiggles are our friend. Where does our else belong to? Does it belong to this if or this if? The interior if. Because again, we are only testing this on numbers that are greater than 2 or equal to 0. We have to make sure we are greater than or equal to 0, otherwise we will have crash and burn and pain. And we want to avoid the crash, burn, pain. Okay, so we have our framework here. I'm going to go over here, and we're going to add our else. This else belongs right here, inside the first if. But it is our else. And this is where recursion happens. So this is a recursive call. And no, this is not the crappy handwriting that I, recursive, whatever. No, recursive call. It's a method. I can't write in cursive, so crappy handwriting. Okay. Else. Do I put a parens on an else? No, because an else does not have a... There's no test. It's just, if I failed the test, do this. Now this is where the code is a little tiny smidge different. Return. return Fibonacci of current number minus 1 plus Fibonacci of current number minus 2. I'm calling my method inside my else statement of my method. If I fail my test, I dig deeper. Now this is not the Shanti insanity dig deeper. This is the dig deeper that I'm going to continue working this method. And so if my current number is 8, I'm going to go back and call Fibonacci on 7 and Fibonacci on 8 minus 2 is 6. And so that means I'm going to have method calls happening. And this is why recursion sucks up so much memory, because watch what happens. So f of 5 right here, we've got f of 5 right there on the screen, you guys can see. And so we have 5. 5 is going to call fib on 4 is going to call fib on 3 is going to call fib on 1 is going to call fib on 0, negative 1, and it's just going to, but then it stops. So 0 and 1, and it's done. But 2 will call it on 1 and 0, because 2 minus that, right? And that'd be actually negative 1 and 0. And so we'll get that done. And then we have, 2, it's going to call it on 0 and 1. And 3 is going to call it on 2 and 1. And 1 is going to call it on 0 and negative 1. And 2 is going to call it on 1 and 0. And 1 is going to call it on negative 1 and 0. So calling fib on 5 calls fib on 4 and 3, calls fib on 3 and 2 and 2 and 1, calls fib on 2 and 1 and 0 and negative 1 and negative 1 and negative 0, and 0, negative 1 and 0, and negative 1 and 0, and 1, 0, and negative 1. So Fibonacci, as a recursive method, will call this. Boom, 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 boom. Because fib on 1 just returns 1. So actually it just returns, excuse, doesn't return that. Yeah, so brain fart there. Like, wait a second. There we go. Like, wait a second. I wrote too many numbers down. Because once we get to 1, it just returns a value. 0 returns a value. So calling fib on this gives how many method calls? So fib on 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now imagine if you call this number on something bigger. Like say fib of 20. Do you see where the lack of efficiency comes into play? Because is this 3 the same as this 3?
No.
Yeah, this whole tree right here is the same as this tree right here. But recursion doesn't care. It doesn't keep track of that. And so recursion just goes through and digs, and digs, and digs, and digs, and digs until it reaches its. When do we stop? Base case. So our base case is 0 or 1. If we don't hit that base case, it keeps on digging. If I took off this if right here and just left it as return Fibonacci number of current number minus 1 to Fibonacci plus Fibonacci of current number minus 2, it keep digging and digging and digging and digging infinitely. And then our system will crash. And although systems crashing, it sounds nice and fun, maybe even noisy, it's not helpful. And so that is why we have to have our base case first. And so our base case again, making sure it's 0 or 1, If it's not 0, 1, right here, because it's a 0, I don't have to subtract, negative 1, negative 2, because I've reached the base case. 0 is a base case. I stop recursive. I just return 1. So let's check this. Fib of 5 is 1 plus 1 plus 1, 1, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. Hey! Fib of 5 is 8! Our math worked! Woohoo! Because every time I get to a 0 or 1, that's just a 1 to add up. And we talked about on the notes how at the base case, that's when I stop generating information and I start gathering the information. So that plus right here, I'm going to start gathering it because I've got down to the spot where I'm returning a single value instead of generating values. When I call Fibonacci of current number minus 1, I'm generating information. I'm calling it again. Once I get down to the base case, I am no longer generating. I now can move back up and gather information. And so I don't gather this information until the end. Now, this is for that last time on your notes, the difference between loops and recursion. So go to that section of your notes. And we all have this done, right? We have our if test and our else results. You have this in your notes? Else return Fibonacci of current number minus 1 plus Fibonacci of current number minus 2. Everybody has that? Oh, you can get a picture, of course. Always. Always get pictures. Yeah, taking pictures of notes is a great tool. I highly encourage it. Okay, so we're going to erase this and add new detail. Okay, so difference. Okay, first a visual difference. Here is a loop. Yes? I'm going over and over and over and over and over and over, and I'm doing the same thing over and over and over again. Right?
Yep.
Even if I'm keeping information, but it's that same basic structure. However, with recursion, I go up. I take information and then I change it. I continue. I change it. 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 I've reached a base case. I have to stop. I then go back and rebuild. At all those change information points. And then I have my answer. A loop, I just keep on doing it until it's done. But I'm not changing my information. In a recursive call, in my else case, I called Fibonacci of number minus 1 and number minus 2. I changed my information. I made a turn. Rather than continuing on in that same circle, in recursion, I'm making a turn. And I'm making a turn on less information in this case. And I go until I reach my base case of either 0 or 1, where I'm at the bottom of my information that I know. And I go back and I build it back up as I have that information that I've already set aside to do it. So recursion is a building process at the end.
A loop just continues gathering that information until it's done. A recursive process, instead of doing that, it goes, takes off a chunk or changes a chunk, and then continues on. Takes off or changes a chunk, continues on, until it reaches the base case, where it then picks up those chunks that it took off or changed to generate its result when it backs its way out. So recursion goes outside of itself. It goes to the stopping point and then builds itself back from those pieces all the way back. Recursion is a different process. Is our code any way different? We have a return statement. We have an if test. We have a method with a value. We've done those tons of times. The difference is we have multiple return options. And the return option of the recursive case is returning a method call. So recursive case, our recursive call, is inside a return statement. So, just a quick little review. We have our base case. A base case is when we do what to the test?
Test it.
We do the if test?
Test it.
Pass the if test. What are we doing at this point after we pass the if test?
Stop it.
We stop. And we then start the collection of info. Because once we reach that base case, we'll start building that information back up because we have part of our answer now. If we are in a recursive case, we're still generating our answer. If failed the if. We return a method call. We return a recursive method call specific. We call our method again, right? So if I'm inside Fibonacci, I call Fibonacci again in my return statement. In my base case, I just return a set value. When I'm in my recursive case, I return a method call. So recursive case, return what? Method call. Everyone make sure it's in your notes. Return case is a method call. My base case, I return a value. My base case, I pass the if, I stop, I start a collection of data, and I return a value. The recursive case, I fail my if, and instead of returning a value, I return a method call. Because the method call goes back and does it again. We generate a tree of information.